Hello everyone. In this lecture, I shall discuss the numerical integration. Basically, I will discuss here the trapezoidal rule, Simpson's 1/3 rule and Simpson's 3/8 rule. Now suppose you are given a definite integral to evaluate a to b fx dx. Now the difficulty arises when this fx is not integrable. Fx is not integrable by usual sense. Or fx is known only at a finite number of points. Means you say here x0 f0, x1 f1 and so on here xn fn. If these tabulated points are known like your interpolation methods. So here otherwise if it is not integrable, then we can split it into the nodes and corresponding functional values. Okay. Now the process of evaluating the definite integral from a set of tabulated values is known as numerical integration. Okay, likewise, when this function is a function of single variable, and this process is called the quadrature. Okay, so here the trapezoidal rule and the Simpson's rule are basically derived from the Newton-Cotes quadrature formula. Okay, so before we have the details of our discussion, let me to introduce myself. Myself, Professor Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Odisha, India. So without much delay, let us now discuss the Newton-Cotes quadrature formula. Generally, the Newton-Cotes quadrature formula is given by integral a to b fx dx is summation of lambda I fxi. I is equal to 1 to n. And our interest is in finding here lambda I. Okay, we find lambda I and substitute here. Where lambda I is equal to minus 1 to the power n minus I divided by n minus I factorial into factorial I h and integral 0 to n s minus s into s minus 1 into s minus 2 so on s minus n divided by s minus I into integral ds. Okay, so now if we are finding for lambda I, it is s minus I. So note that here the nodes are equispaced. That means xi is equal to x0 plus ih, and here I is equal to 0, 1, 2, so on here n. Okay. Similarly, if I ask you what is your xn, it is x0 plus nh, or h is equal to xn minus x0 by h. Okay, so accordingly here we are considering the equispaced points. Now this is the important formula for n is equal to 1. Okay, if we put n is equal to 1, then it leads to trapezoidal rule. Means we have here two nodes x0 and x1. If n is equal to 2, then it leads to Simpson's 1/3 rule. Means here we have x0, x1 and x2. We have three nodes. Likewise, if we have our n is equal to 3 means x0, x1, x2, x3. With these nodes, it leads to Simpson's 3/8 rule. Okay, so let us now discuss the formula for the trapezoidal rule, Simpson's rule and Simpson's 3/8 rule by substituting n is equal to 1, n is equal to 2 and n is equal to 3 here respectively. Now coming to the trapezoidal rule. Here n is equal to 1 here. Okay, so for n is equal to 1, here integral a to b fx dx will be here lambda 0 f0 plus lambda 1 f1. We need to find what is lambda 0 and what is lambda 1. So here lambda 0 is equal to, means here n is equal to here 1, but I is equal to 0. And if you substitute this here in lambda I, then your lambda 0 is minus 1 to the power 1 minus 0 h 1 minus 0 factorial integration 0 to 1 here s into s minus 1 divided by s minus 0 ds, and you evaluate the integral, it will be minus 1 to the power 1 means minus of h, and in the denominator it is 1, 0 factorial is 1, and integral 0 to 1, here s and s cancelled, it is s minus 1 ds, and you simply integrate it. It is here, this is equal to your minus of h, and integral of s is s square by 2 minus s 0 to 1. So this is equal to minus of h 1 by 2 minus 1. So this is equal to h by 2. So therefore we are getting lambda 0 is equal to h by 2. Likewise we find lambda 1, and for your lambda 1, what is your lambda 1? Here we are substituting n is equal to 1, I is equal to here 0. Okay, I is equal to 1, I is equal to 1. So now substituting this, your lambda 1 will be minus 1 to the power 1 minus 1 into h by 1 minus 1 factorial into 0 factorial integral 0 to 1 s into s minus 1 divided by s minus 1 divided by your s minus 1 divided by s minus 1 ds. Now this here s minus 1 cancelled here, and it will be equal to minus 1 to the power 0 is 1, it is h only, integral 0 to 1 s ds. Okay, so this is equal to h into s square by 2 0 to 1. So this is equal to here h by 2. So therefore we are getting lambda 1 is equal to is also here h by 2. Okay, and here lambda 0 is also h by 2 and lambda 1 is also h by 2. Now we substitute here. So therefore by trapezoidal rule, the necessary formula here is integral a to b fx dx is same thing as here x0 to x1 fx dx is equal to h by 2 f of x0 plus h by 2 f of x1. Okay, f of x1. So this is the formula, or we write h by 2 f0 plus f1. Okay, so this is the necessary formula for your trapezoidal rule. x0 to x1 fx dx will be this. If we want to write in terms of AB, then if I want to write it in the form of AB, so h will be what? H will be simply this gap. H will be simply the gap of x1 minus x0. This is my b minus a. So I will able to write it. It is b minus a by 2. It is f of a plus f of b. Or I may write it in this way. Okay. Or I may write it in this way. Right. And it is better we should write it in this way so that we can extend it towards the generalization. Now for Simpson's 1/3 rule, here n is equal to here 2 here. Okay. So for n is equal to 2, here integral I is a to b f dx becomes here x0 to x3 f dx. Okay, fx dx will be summation of I is equal to 1 to 3, 0 to 2, here lambda I fx I. So this will be lambda 0 fx0 plus lambda 1 fx1 plus lambda 2 fx2. Okay, so now we need to find the value of lambda 0, lambda 1 and lambda 2. Now if you simplify it, your lambda 0 will be h by 3, lambda 0 will be h by 3, and your lambda 1 will be 4h by 3, and your lambda 2 will be h by 3. Means here we are substituting n is equal to 2, I is equal to 0, n is equal to 2, I is equal to 1, and here substituting n is equal to 2, I is equal to 2, and if you simplify, we will get it. Now if you substitute it here, then the formula will be, so therefore the necessary formula for Simpson's 1/3 rule is integral x0 to x2 f dx is equal to h by 3 here f0 plus 4f1 plus f2. If we want to write in terms of a and b, it will be, if we want to write it in terms of a and b, here integral a to b fx dx. So here a is equal to here x0, b is equal to here x2, means we have x0, x1 and x2. This gap is h and this gap is h. Okay, so what is here h? H is equal to this minus this by 2, x2 minus x0 by 2, means b minus a by here 2 here, means x1 is a midpoint here. Okay, and what is here x1? x1 is equal to x0 plus h. What is here x2? It will be x0 plus 2h, and if you simplify it will be a plus b by 2. So it will be h will be by b minus a, so it is b minus a by 6. B minus a by 6, it is f of a plus 4 f of a plus b by 2 plus f of b. Okay, so this is the formula in terms of a and b, but we should prefer this. Now for Simpson's 3 by 8's rule, we have n is equal to 3, means we have here x0, x1, x2, x3. Okay, f0, f1, f2, f3. Accordingly, we will split it. So here a to b f dx is x0 to x3 f dx is summation of lambda I fi. I is equal to 0 to 3. So this will be lambda 0 f0 plus lambda 1 f1 plus lambda 2 f2 plus lambda 3 f3. Now likewise, if we simplify, here lambda 0 will be 3h by 8. Lambda 3 will be 3h by 8, and here lambda 1 will be 9h by 8, and also lambda 2 will be 9h by 8. Okay, if you simplify it, so this will be 3h by 8 taken common, it will be f0 plus 3 f1 plus 3 f2 plus f3. Okay, so this is the formula x0 to x3 f dx. So this is the formula for your Simpson's 3 by 8th rule. Okay, if you want to view in terms of a and b, this is your a and this is your b. So this is h, this is h, and this is h. So h is equal to b minus a by 3. Accordingly, here x1 is equal to x0 plus h, x2 will be x0 plus 2h, and x3 will be x0 plus 3h. Accordingly, we can write the formula in terms of a and b, but we need it. Okay, now coming to the working rule for problems. Now coming to the composite or generalized trapezoidal, Simpson's 1/3 and Simpson's 3 by 8th rule. And basically these are used to solve the problems. Okay, these things are used to approach the problems. Basically use the generalized formula to solve the problems for better accuracy. Okay, so we are interested in finding the composite or the generalized formula. Now coming to the trapezoidal rule. Now for the composite trapezoidal rule, we have here interval a to b is here x0 to xn. We split it like this. We split it x0 to x1 union x1 to x2 union x2 to x3, right? Likewise it is union xn minus 1 to xn, because basically in the usual formula we need two nodes. You see here in each interval we have two nodes. Now here, now in individual intervals we find integral here x0 to x1 f dx by usual trapezoidal rule is h by 2 f0 plus f1. Okay, as we see here your trapezoidal rule h by 2 f0 plus f1. Now similarly if we take integration of x1 to x2 f dx, it will be h by 2 f1 plus f2. Likewise here x2 to x3 f dx will be h by 2, here f2 plus f3, lower plus upper, and if we go on continue, and it will be xn minus 1 to xn f dx, it will be h by 2 fn minus 1 plus fn. Now if you add it, you see, if we add it, this is x0 to x1, then 1 to 2, then 2 to 3. In the left hand side it will be here x0 to xn f dx, In the right hand side it will be f0 is once, fn is once, but f1 is twice, f2 is twice, likewise fn minus 1 will be twice. So h by 2, it is f0 plus twice the intermediates f1 plus f2 plus fn minus 1, okay, plus fn. So this is the formula here. Composite trapezoidal rule, the formula for composite trapezoidal rule. So likewise for composite Simpson's 1/3 rule, you have A to B is your x0 to xn, you split it in this way. It is x0 to x2 as we did it earlier. Then accordingly next will be x2 to x4, then next will be x4 to x6, you go on continue, it will be xn minus 2 to xn, okay. You see here we need n must be even here, okay, n must be even here, because you see 2 4 4 6, n must be even, means multiple of 2, but here we don't need. N may be even or odd, n may be anything, even or odd, whatever it may be, no restriction is here. But for Simpson's 1/3 rule, we must have n is even, most important. So now in individual subintervals, okay, we apply the Simpson's formula as we did it earlier. So here integral x0 to x2 f dx will be h by 3 f0 plus 4 f1 plus f2. Already we did it. Likewise here we have x2 to x4 f dx will be h by 3 here f2 plus 4 f3 plus f4. Then here x4 to x6 f dx will be h by 3 f4 plus 4 f5 plus f6. If we go on continue, it will be xn minus 2 to xn f dx. It will be h by 3 fn minus 2 plus 4f n minus 1 plus fn, okay. Now if you take the union of this, so here you see x0 to 2, then 2 to 4, and sequentially here it will be x0 to xn f dx will be, if you add it, f0 is single, fn is single, and this 2, this 4, right, and this n minus 2, these are double, right. So this will be h by 3, it is f0 is single, and here 2 times f2 plus f4 plus f6 up to plus fn minus 2, okay. Then here 4 times f1 f3 f5 fn minus 1 plus 4 times f1 plus f3 plus f5 plus up to here fn minus 1, and the last one is the single fn, okay. So this is the necessary formula for Simpson's, generalized Simpson's 1/3 rule. Here note that n must be here even, okay. Accordingly we will discuss the Simpson's 3/8 rule. Now coming to the generalized Simpson's 3/8 rule, basically here n must be the multiple of 3, okay, multiple of 3, right. So n must be 3, 6, 9, 12 like that, right. So now coming to this rule, we have x0 to xn, here a to b is same thing as x0 to xn, and we split it x0 to x3, then x3 to x6, then x6 to x9, likewise you have your xn minus 3 to xn. Okay, n is a multiple of 3 here. Now in this interval we know the formula, already we know the formula here, Simpson's 3/8 rule for x0 to x3. So accordingly in each interval we will find a formula. So here x0 to x3 f dx is equal to 3h by 8 f0 plus 3f1 plus 3f2 plus f3. Then x3 to x6 f dx will be 3h by 8 f3 plus 3f4 plus 3 f5 plus f6. Okay, then x6 to x9 f dx will be 3h by 8 here f6 plus 3f7 plus 3f8 plus f9. If we go on continue, it will be xn minus 3 to xn f dx will be 3h by 8 fn minus 3 plus 3 fn minus 2 plus 3 fn minus 1 plus fn, and finally if you take the union, it will be x0 to xn f dx will be 3h by 8. You see here, it is 3 times this f3 will be twice, f6 will be twice, and here fn minus 3 will be twice. It is 3h by 8, 3h by 8 taken common, it is here 3h by 8 taken common, it will be f0 plus 2 times 3, 6, 9, so on fn minus 3, and the last one is single. Okay, and the middle one 1, 2, then 4, 5, these are all 3 times, right? Then plus remaining 3 times here f1 plus f2, f3 is here, then here f4 plus f5, f6 is here, and here f7 plus f8. If you continue, it will be up to here fn minus 2 plus fn minus 3, and the last one is single, last one is here fn. Okay, so this is the necessary formula for Simpson's 3/8 rule. Now coming to a general remark, for generalized trapezoidal rule we need n is even or odd, anything. For Simpson's 1/3 we need n is even. For Simpson's 3/8 we need n is a multiple of 3m, multiple of 3. Now if all this rule to work simultaneously, if I take n is equal to 6, if I take n is equal to 12, right, if I take multiple of 3, so here it is 2m. So now if it is the LCM is 6, so it multiple of 6, it will work for all the formula. Okay, n is equal to 18 and this rule will work. Now for n is equal to 12, let me to write these 3 formulas. Now for n is equal to 12, say, right, what will be your trapezoidal rule? The trapezoidal rule will be integral x0 to x12 f dx will be here h by 2 f0 plus 2 into f1 plus f2 plus up to f11 plus f12. Okay, then here Simpson's 1/3 rule will be here x0 to x12 f dx will be h by 3, it will be f0 plus 2 times f2 plus f6 plus f8 plus f10 plus here 4 times f1 f3 f5 f4 f5 then f7 f. So there is a little correction here, the even terms are there, it is f2 then 4 then 6 then 8 then 10. Okay, f12 is single, it is outside single, and remaining 4 times plus 4 times 1 3 5, 5, 7, 9 and 11. Okay, this is this. So here F0, then 2 times the evens and 3 times the odds here and the last one. Okay, so this is the formula. Likewise, for your Simpson's 3 by 8 rule, it will be, so for Simpson's 3 by 8, it will be 3h by 8. First one is single F0 and 2 times the multiple of 3 means 3, 6, 9 and here 3 times the remaining 1, 2, 4, 5, 7, 8, then 10, 11 and the single is here last one F12. So this will be the formula. So for n is equal to 12, all these 3 formula work simultaneously. Okay, simultaneously all these 3 formula will work. So now you are asked an example. Use trapezoidal rule, Simpson's 1/3 rule and Simpson's 3 by 8 rule also to evaluate this integral. Evaluate this integral. I is equal to this and estimate the error in each case. So you see here, coming to the solution. So the interval of integration here is 0 to 6. So is 6 here. If you subdivide into 6 equal parts, so here if we take n is equal to 6 here, then all these 3 formula will work. Trapezoidal rule, Simpson's rule, both will work. All these 3 formula will work. So what will be your h? H will be 6 minus 0 by 6 will be your 1. Okay. Here the interval of integration is, 0 to 6. We subdivide it into 6 equal parts. We subdivide it into 6 equal parts. That is, my n is equal to 6 and h is equal to b minus a by 6 is 6 minus 0 by 6 is equal to 1. It is my AB. So this is my h is equal to 1. So now I tabulate the data. Consider the table. We have x is 0, 1, 2, 3, 4, 5, 6. This is our x and our fx is equal to here 3x square. So it is here 3 into 0 square 0 and 3 into 1 square 3, then 3 into 2 square is 12, then it is 27, it is 48, it is 75, it is 108. Okay, so this is my tabulated data. This is my F0, F1, F2, F3, F4, F5, F6. Okay, so now come to the formula. It will be here h by 3 F0 plus 2 into F2 plus F4 plus 4 into F1 plus F3 plus F5 plus F of 6, isn't it? So this will be here h is 1 by 3 F0 is 0 plus 2 into F2 plus F4, 12 plus 48 plus here 4 into 1 is 3, F3 is 27 plus F5 is 75 plus last one is 108. If you simplify it, it will give you 216. Okay, so now let us solve it by Simpson's 3 by 8. So the formula will be 3h by 8 F0 plus 2 times F3 plus 3 times F1 plus F2 plus F4 plus F5 plus F6. You substitute all this thing, it will give you. So if you simplify it, it will give you, substitute these values, I will get it. If you simplify it, here h is here 1, so 3 by 8, it will give you 216. Now if you have your actual integration, now by actual integration theoretically it is integration of 0 to 6 3x square dx is equal to 3x cube by 3 and here 0 to 6. So this is 6 into 6 into 6 is 216. So what is the error here? So error by the trapezoidal rule, the error here is here 219 minus 216 is equal to here 3. Error is 3 here, but the error is 0. 216 minus 216. Actual minus approximate. Here what is the error? The error here is I actual minus I approximate. This is what we are getting approximate. Okay, this is what we are getting approx, means numerically we are doing it. Okay, this is my approx, this is approx, and this is also approx, but this is your actual, actual. Okay, so I actual my I approx, so I can take the mode here 0, right? So the Simpson's, the error here is, so the error is I actual minus I approx. I can take mode to avoid the negative sign. So here the error is 0, and here the error is also 216 minus 216 is 0. Okay, so this is the better one. Okay, but here in case of this, the error is more. However, this is approximate, this is accurate for polynomial of degree, less than equal to 1, right? And however, this is exact for polynomial of this degree less than equal to 3. Since we are evaluating, this is a polynomial of degree 2 here. Okay, polynomial of degree 2 here. So there is no error here because it is exact for polynomial of degree less than equal to 3. So what we call the degree of precision here. Degree of precision. Precision is 3 here. Okay, degree of precision is 3 here. Here also Simpson's 1/3 rule. The degree of precision is 3 here. Means it is correct up to polynomial of degree 3. Okay, but here it is the degree of precision for trapezoidal rule is 1 because it will correct up to the polynomial of degree 0 and 1. Okay, and there will be no error. If instead of 3x square, if we have 3x dx, there will be no error in trapezoidal. If 3x5 is there may be some error in Simpson 3/8 and Simpson's 1/3 rule. So coming to one more example, you are asked to evaluate this. So your fx is your 1 by 1 plus x. Okay, and the limit of integration is 0 to 1, interval of integration is 0 to 1, and we are asked to solve this by using Simpson's 3/8 rule. So we need n is a multiple of 3. Okay, so since it is Simpson's 3/8 rule, we need n is a multiple of 3 here. So let n is equal to 6. Okay, let n is equal to 6. So this implies my h will be 1 minus 0 divided by 6 is 1 by 6. So if I tabulate the data x fx, if I tabulate the data, then my tabulated data will be like this. If it is 0, then it is 1 plus 0. It is 0, 1, 2, 3, 4, 5, 6. It is 1 by 1 plus 1, 2. It is 1 by 3. It is 1 by 4. It is 1 by 5. It is 1 by 6. It is 1 by 7. So actually there is a calculation mistake here. So here it will be x0 is 0 and x1 will be x0 plus h means 1 by 6. It will be 2 by 6. It will be 3 by 6. It will be 4 by 6. It will be 5 by 6. It will be 6 by 6 means here 1. Then accordingly here f will be 1 by 1 plus 0 1. It is 1 by 1 plus 1 by 6 means 6 by 7. It is 3 by 4. It is 2 by 3. It is 3 by 5. It is 6 by 11 and it is 1 by 2. Okay, so this is my f0, f1, f2, f3, f4 f5 f6. Accordingly, I use the formula here. We have the Simpson's 3 by 8 rule. By Simpson's 3 by 8 rule, we have integral x0 to x6 f dx, and here it is 0 to 1 f dx will be here 3h by 8. Here first one is single, last one is single, f0 plus f6. Then it is 2 times here f3 plus remaining will be here 3 times f1 plus f2 plus f4 plus f5. If you simplify it, it will give you here h is here 1 by 6. So it is 3 into 3 by 3h by 8. 8 into 6. And it will be 1 plus half if I substitute it, plus 3 into 6 by 7 plus 3 by 4 plus 3 by 5 plus 6 by 11, okay, and plus 2 into f3 will be 2 into 2 by 3. If I simplify it, it will give me 0.6932, okay. So therefore 0 to 1 dx by 1 plus x is equal to 0.6932. This is my approx, because we are approaching by numerical integrations, okay. But by actual integration will be integration 0 to 1 dx by 1 plus x. It is ln 1 plus x, okay, 0 to 1. So this will be ln 1 minus ln 2 minus ln 1. Ln 1 0 is here ln 2. The actual value of ln 2 is, so the actual value of ln 2 is 0.6931471. However, we are asked that use numerical integrations, you approximate the value of log 2. That means here log 2 is approximated to this. Therefore, we can say, right, the approximation of ln 2 from the given data is 0.6932, okay. If we will be asked to find the error, then we may take the difference of these two. So now coming to the solution of example 3, you are asked to use Simpson's 1/3 rule to evaluate this, okay. So here I is equal to let 2 to 8 dx by log, it is 1 by log x to base 10 dx. You see, it is not integrable. It is not integrable in usual sense. Not integrable, okay. So we use here the numerical rule here. So in Simpson's 1/3 rule, we need n is even. Okay, n is even. So if I take, so our hands are open, okay. We may take n is equal to 2, 4, 6, 8, whatever it may be, 10. If I am taking for n is equal to 6, then this h is a better one. I have h will be 8 minus 2 by 6 is equal to 1, okay. Now I tabulate the data x, and my fx is 1 by log x to base 10. So let me to just tabulate the data. So it will start at 2 and increase by 1. So it is 2, 3, then 4, then 5, then 6, 7 and 8. Accordingly, the functional value here will be 3.3219. It will be 2.0959. It will be 1.661. It will be 1.4307. It will be 1.2851. It will be 1.1833. It will be 1.1073, okay. And it is here f0, f1, f2, f3, f4, f5, f6. So you apply the formula now. By Simpson's 1/3 rule, integration of a to b f dx will be here h by 3 f0 plus 2 into f2 plus f4 plus 4 into f1 plus f3 plus f5 plus here f6. If you substitute all this value here, and it will be here 9.7203. Okay. However, it is not integrable in usual sense. So the usual method to find the error will not work. There will be a separate error formula to be discussed later. So for error here, you see here, so now we get it, but it is not integrable in usual sense, not integrable. So for error, we need separate formula, different formula we need, different formula, right, different formula to be studied. Now we'll discuss the geometrical interpretation and error formula. Now coming to the trapezoidal rule, trapezoidal rule, you are asked to evaluate the integral a to b fx dx, means the geometrically the curve is given like this. This is the curve, y is equal to fx is given to you, and this is your a and this is your b. So you are asked to find this area. Okay, you are asked to find this area actually, but what we are doing by the trapezoidal, we are just joining a chord here. Okay, joining a chord here. Let it be my C and D. So now we just find the area of this trapezium. Okay, we just find the area of this trapezium here. So this is the geometrical interpretation and it is named as this. However, this part is my error now. So now this part is my error now. Okay, so what is the geometrical interpretation? The area under the curve, this is my y is equal to fx, is replaced by the area under the, this is the area under the trapezium, right? This is the area under the trapezium, right? So that's why the rule is named as trapezoidal rule. So let me to write. So coming to the geometrical interpretation, so the area under the curve y is equal to fx is replaced by the area under the trapezium. Okay, this trapezium. So ABCD I say, ABCD I say, ABCD, trapezium ABCD. That's why this method is named as the trapezoidal rule. Okay, and this rule, as you see in example 1, is correct up to the polynomial of degree 1. Okay, so that means the degree of precision of trapezoidal rule is 1. Now coming to the coming to the geometrical interpretation of Simpson's rule. In Simpson's rule, actually, suppose you are given a curve y is equal to fx. The curve is given like this. Suppose the curve is given like this. Okay, the curve is given like this. So we have 3 points we are taking here. We just take a parabola. Basically for trapezoidal Simpson's rule, Simpson's 1/3 rule I say. This is 1/3 rule. Okay, we need x0, x1 and x2. So we have a curve. Y is equal to fx is the curve given here. Now we replace this curve by a parabola passing through these 3 points. Okay, passing through these 3 points we take a parabola. So now the area under the curve is same thing as the area under the parabola. Okay, the area under the parabola, right? The area under the parabola, it is AB. So now the error here is so this person is left. Okay, this person is left. So this person will lead you to the error. So that means the area under the curve is replaced by the area under the, this is now a parabola. So this is what the geometrical interpretation. So the geometrical interpretation of your Simpson's 1/3 rule is that the area under the curve y is equal to fx is replaced by the area under the parabola, and this method is correct up to polynomial of degree 3. If you integrate a third degree polynomial by this method, the error is 0. So we say the degree of precision of Simpson's 1/3 rule is 3. Likewise, the degree of precision of Simpson's 3/8 rule is also your 3. Now coming to the error. Now coming to the error formula, your error is equal to I actual integration minus I approximate. Right, modulus we can take to avoid the negative sign. But this I actual is not that easy. Is not easy always. In fact, not possible. Sometimes. Then what to do? Then we have a error formula. So what is that error formula? The error formula Rn is equal to integral a to b fx wx dx some weight minus, as we did in Newton Cotes quadrature formula, lambda I fx I is equal to 0 to n. Here in the quadrature formula we need, and generally here we are taking wx is equal to 1 we are taking, and if you simplify it, this error will be h to the power n plus 2 divided by factorial n plus 1 integration of x0 to xn s into s minus 1 into s minus 2 so on so on so on s minus n f n plus 1th derivative at some point zeta, and it is ds. Okay, now zeta is a point in between your x0 to xn, x0 to xn. Okay, and this is the error formula. This is your error formula. Now for trapezoidal rule, the error formula is, for trapezoidal rule your error formula is Rn is equal to error, Rn is equal to, if you work out it, here n is equal to 1 here. Okay, n is equal to 1 here. If you substitute here, your error will be given by Rn will be minus of h cube by 12 f double dash zeta, or it is minus of b minus a whole cube by 12 f double dash zeta. This is the error. You see here, you see one more thing. So since the error formula involves the second order derivative, right? So for polynomial of degree 1, right, f double dash zeta is tends to 0, equal to 0. That's why the Rn error is here 0. So this degree of precision of trapezoidal rule is 1. So for Simpson's, for your trapezoidal rule, we are taking n is equal to 1. The error e, or I can write it R2 here is this h minus h cube by 12 this, and the degree of precision here is here 1. Okay, as I told that f double dash zeta means second derivative once 0 for polynomial of degree 1. That's why the degree of precision is the degree of precision is 1. So for Simpson's 1/3 rule, here n is equal to 2. If you simplify it, your error will be here, it is here R1 here. In Simpson's rule, the error is R1 here. Okay, it is R1, and here it is R2 will be, if you simplify it, it will be minus of h5 by 90 f fourth derivative at zeta. Okay, and here a less than zeta less than b. This is the interval of integration. You see here, since this fourth order derivative is involved, so it is correct up to, right, this derivative will tends to 0. Polynomial of degree less than equal to 3, right? It is exact for that's why the degree of precision for Simpson's 1/3 rule is at 3. So for Simpson's 3/8 rule, here n is equal to here 3. Okay, and here Rn is equal to R3 will be what? H to the power n plus 2 here divided by n plus 1 factorial integral, this is integral 0 to 3 s into s minus 1 into s minus 2 into s minus 3. It is f of fourth derivative at zeta ds. Okay, if you simplify it, it will be my minus of h, it is minus of 3h to the power 5 by 80 f iv zeta. And what is your h here? H is b minus a divided by 3 here. And what is x3 here? x0 plus 3h. Okay, so now this will be my error formula here. And you see in this formula we find the fourth derivative here, so it is correct up to third degree polynomial. That's why the degree of precision for Simpson's 3/8 rule is also 3. Okay, so let me to conclude. So to conclude, the trapezoidal rule or the Simpson's 1/3 and 3/8 rules are derived from the Newton-Cotes quadrature formula. However, in order to solve the problems, we should use the generalized formula to minimize the error. And note that for trapezoidal rule, n may be even or odd, as many as partitions we need to minimize the error. In Simpson's, we have even number of partitions we need, and for Simpson's 3/8 rule, we need multiple of 3 number of partitions. Okay, and the Simpson's 1/3 rule and 3/8 rule are exact for polynomial of degree 3 up to 3. So that's why the error in that case is less in comparison to trapezoidal rules, as we have seen in example 1. Okay, so now with this the video is getting lengthy, we should close it here. Okay, and my appeal at this stage to all of you is that if this video is interesting and useful for you, please like and subscribe to this channel. This will boost my motivation and which will help me to upload subsequent lectures for your benefits. Thank you all. Have a nice day.